In the next set of videos, I'm going to take you through a technical tour of the problems we will solve as part of this course. You will see a lot of MATLAB codes therein. The idea here is not to get into the mathematical and numerical methods behind these problems, but just to show you the outer shell of how the problems are solved using MATLAB. After these set of video segments, we will get into the numerical methods and look under each of the problems what kind of numerical methods are adapted. So let's get on with the technical tour of the models. So if you take a look at the course contents, we would see something like, MATLAB fundamentals that has to be completed or that has to be learned, and we are doing some aspects of that. I had a session talking a little bit about MATLAB command window, a few commands and so on. So we have done that a little bit. And we have also got some practice using the problems that were assigned to you, right? Either in the form of tutorials or as assignments, we are trying to weave in MATLAB into it. So this set of videos that we are going to look at will also take us further along those directions. So we also will have to learn the basics of linear algebra, which we will get to in the next set of videos. But then from here on, from item 3 onwards, we are going to look at different classes of problems that we will discuss. We will start off by discussing the solution of a linear system of equations. So this is the basic thing that we know to solve correctly. And as I said in one of my earlier videos, everything else that follows will utilize the solution of Ax is equal to b at some stage. So we are going to start by looking at methods of solving Ax is equal to b. Then we will get into the solution of a single nonlinear equation. So you have one nonlinear equation with one unknown. So we would try to find out the root or the roots of a single nonlinear equation, because nonlinear equation can have multiple roots. For example, a quadratic equation has two roots, and some equations will have more than two roots. In fact, the idea will be to find out as many roots as possible, right? So sometimes we do not even know how many roots certain equation has. So at least we will try to find out one physically meaningful root of a single nonlinear equation. And then we will extend those ideas to systems of nonlinear algebraic equations. This is going to be very important because many equation systems are going to be nonlinear. When I talk about equation systems, basically you're going to have more than one equation, and that equation or those equations will also be nonlinear in nature. So solution of nonlinear algebraic equations, a system of them, is going to be very critical for making progress. Then we will get into optimization, right? The optimization problem where we can maximize or minimize an objective function. For example, we can learn to maximize profit. We can learn to minimize environmental impact. We can learn to minimize cost, things like that, right? So, and to minimize cost or to maximize profit, we always have some handles, right? So we have to find out what are the right levels of those handles that will help us achieve the objective. Then we will look at interpolation. This problem is something that we know. Let's say we know the value of the function at 3 points, x1, x2, and x3. x1 is, let's say, -1, x2 is 0, x3 is +1, just as an example. So the corresponding values of y are y1, y2, and y3. Let's say this is 0.74, 0.19, and let's say 1.24. I'm just pulling some numbers randomly. Let's say these are the values. Now we are asked the question, what's the value of y at x is equal to 0.42? So this is what is called the interpolation problem. All right. So we have to make use of this data and come up with the best estimate of y at x is equal to 0.42. And there are different ways of doing that. Then we will look at numerical integration. That means integration of functions f of x dx. Let's say between limits x1 to x2. Let's say we have to evaluate these integrals. I'm just taking one function, right, in one variable x, but you can extend it to multiple integrals if you want. But let's say we want to integrate this, and we have done it in high school and so on, right? Integrating functions, we have been taught a few techniques, and we can solve easy as well as slightly complicated problems. But let's say the function f of x is very hard, right? You cannot solve it using the analytical techniques that were taught to you in high school or at the university. Then we have to resort to estimating this integral using numerical methods. So there are many approaches possible to evaluate this kind of an integral, right? So that is why it is called numerical integration as opposed to analytical integration. Analytical integration, you will solve it by hand using several of the techniques and tricks that were taught to us. But if the function f of x is complex, then we have to resort to numerical techniques and find the value of this integral. As you know, this is called a definite integral because you're integrating between x is equal to x1 to x is equal to x2. All right. And there are lots of chemical engineering applications for these kinds of problems. For example, in reactor design. Then we will get on to what is called numerical differentiation. Numerical differentiation is given some data or some function f of x, you want to find out df by dx or d squared f, the second derivative with respect to x squared, etc. Right? So this is what we are going to do. Again, we are going to adopt a numerical approach because calculus will tell us if the function is quite simple, then calculus will tell us how to differentiate it, right? So we have the chain rule, we have the quotient rule, we have all those kinds of things for differentiating functions. But if you have to solve it numerically, right? That means not analytically because the problem is hard, then you have to resort to this numerical differentiation, and we will learn a lot of this. Now, this is going to become very, very critical in solving ordinary differential equations of the initial value type or the boundary value type. Because we are going to take the ordinary differential equations and we are going to replace them by their approximate algebraic equivalence. So we are going to convert an ordinary differential equation into a system of algebraic equations and then solve it. So that is where the things that we discuss in numerical differentiation will become quite useful. But there are MATLAB functions for these things. So in this set of videos for this week, we are going to look at MATLAB, right? The commands that can be used to solve problems of the initial value type and the boundary value type. I will explain what these problem types are so that you get an appreciation for it. And the idea is basically to get started with MATLAB, right? I do not want to wait till the end to introduce these problems and the associated commands in MATLAB. So I want to put it up front so that you have an understanding of the kinds of codes you have to write, the kinds of problems you'll be expected to solve, and the MATLAB codes you can use very easily to get the solutions and plot the solutions, discuss the solutions, etc. And if time permits, we will get into some advanced methods for solving the ordinary differential equations, right? So that is the overall scope of this course. So in the next few videos, we will look at each of these problem types, starting from type 3, I believe, to type 11 that is listed here, right? So we will probably not go in the exact sequence that it is mentioned here, but we will nevertheless cover one example of all these problem types and the associated MATLAB commands, etc. Thank you for your time.